For the next few minutes, you're going to discover why one of the most familiar ideas in science, gravity, may not be what you think it is at all. You'll see why the simple explanation we learn in school works for everyday life but hides a far deeper reality, and how understanding gravity properly changes the way we look at motion, space, and even the structure of the universe itself. Before we begin, make sure to subscribe to the channel and click the bell icon so you don't miss more clear, fascinating explanations that turn complex science into something you can truly understand and enjoy. You probably think you understand gravity already. Step onto a scale, see the number and call it your weight. Earth pulls you downward. Drop an object and it falls. The moon circles Earth, planets orbit the sun, and everything with mass attracts everything else. Newton explained it centuries ago, and his idea seems simple enough. Gravity is a force pulling objects together, clean, logical, complete, except it isn't. Not slightly incomplete, but fundamentally wrong about what is really happening. Stand up for a moment and pay attention to what you actually feel. You say you feel gravity pulling you downward, but examine the sensation carefully. The pressure you notice is not a pull. It is the floor pressing upward against your feet. That upward push is the only physical sensation you experience. You never feel a downward pull directly, not once. Gravity, the supposed force pulling you toward Earth, is something you infer, not something you sense. What you truly feel is resistance, the ground preventing motion. That observation already hints that something deeper is going on. Now consider the moon. At this very moment, the moon is falling toward Earth. It has been falling for billions of years, yet it never crashes into us. Instead, it endlessly circles, always falling but never arriving. What kind of force behaves like that? A pull that continuously acts, yet never completes its job. According to Newton's theory, gravity works instantly across empty space. If Earth moved slightly, the moon would supposedly feel the change immediately. But how could that happen? What carries the influence? Newton himself admitted he had no answer. He described gravity mathematically, but confessed he did not understand its mechanism. Still, the predictions worked perfectly. The equations described planetary motion with astonishing accuracy, and for generations, scientists accepted the success without questioning the deeper mystery. But science advances precisely when someone refuses to stop asking uncomfortable questions. Long before Newton, astronomers struggled to understand how planets moved. Copernicus proposed that planets orbit the sun rather than Earth, but knowing what happens is different from knowing why. Tycho Brahe devoted decades to careful observation, measuring planetary positions night after night with extraordinary precision. Real science begins with careful observation. Those measurements passed to Johannes Kepler, who sought the exact shapes of planetary paths. He initially assumed circles, the most perfect geometric form known at the time, but the data refused to cooperate. Mars deviated slightly, only 8 arc minutes, a tiny difference most would ignore. Kepler did not. He trusted the observations more than his assumptions. After years of work, he discovered the truth. Planets move in ellipses, not circles, with the sun positioned at one focus. The match with observation was exact, yet a deeper question remained unanswered. Why ellipses? Meanwhile, Galileo studied motion on Earth using simple experiments. He rolled balls down inclined planes and observed how they sped up. When allowed to roll onto flat ground, the balls continued moving instead of stopping immediately. This contradicted common belief at the time. People assumed motion required constant pushing and that objects naturally came to rest. Galileo realized the opposite was true. Motion in a straight line requires no explanation at all. It is the natural state. What needs explanation is change, slowing down, speeding up, or turning. This idea became inertia. An object in motion continues moving straight unless something alters its path. And that insight created a new puzzle. Planets should travel in straight lines through space. Yet they constantly curve around the sun. Something must be changing their direction every moment. Newton identified that influence and named it gravity, a universal attraction between masses that bends straight motion into curved orbits. With that single idea, the motion of apples and the motion of moons suddenly followed the same rules, uniting heaven and earth under one system of physics. Newton's insight transformed science almost overnight. He realized that planets are not circling the sun because they are somehow guided along invisible tracks. Instead, they are constantly falling toward the sun while simultaneously moving sideways. Their forward motion keeps them from crashing inward, while gravity continuously bends their path. The result is an orbit, a delicate balance between motion and deflection. Kepler's mysterious ellipses suddenly made sense. They were not arbitrary shapes, but the natural outcome of inertia combined with gravitational attraction. The same reasoning explained the moon's motion around Earth. The moon is not suspended in space or held up by anything. It is falling, just like an apple dropped from a tree. The difference is speed. The moon moves sideways fast enough that as it falls toward Earth, Earth's curved surface drops away beneath it. It keeps missing the ground. Falling endlessly becomes orbiting. Newton even calculated how far the moon falls every second and compared that value with how objects fall near Earth's surface. After accounting for distance, the numbers matched perfectly. The force pulling an apple downward was the same force governing celestial motion. For the first time, the physics of the heavens and the physics of everyday life became one unified system. With this law of gravity, countless mysteries suddenly became understandable. Ocean tides occur because the moon's gravitational influence pulls unevenly on Earth's oceans. Earth bulges slightly at the equator because rotation alters how mass distributes itself. Comets follow predictable paths because they obey the same gravitational rules as planets. Even subtle irregularities reveal deeper truths. Astronomers noticed that Jupiter's moons sometimes appeared earlier or later than expected. The explanation turned out not to involve gravity at all, but the speed of light. Light takes time to travel, and when Earth is farther from Jupiter, the signals arrive later. This observation allowed scientists to measure the speed of light for the first time. Newton's theory also revealed hidden objects before anyone could see them. Slight disturbances in Uranus's orbit suggested another planet exerting gravitational influence. Astronomers calculated where that unseen object must be and pointed their telescopes there. Neptune appeared almost exactly where predicted, a triumph of mathematical reasoning guided by gravitational theory. For more than 2 centuries, Newton's description of gravity stood as one of the greatest achievements in human thought. It worked everywhere people looked. Yet one small detail refused to fit comfortably within the theory. If gravity pulls harder on objects with greater mass, then heavier objects should fall faster than lighter ones. A hammer should reach the ground before a feather. But when air resistance is removed, both fall together perfectly. In a vacuum, they strike the ground at exactly the same moment. This result is not approximate. It is exact to extraordinary precision. Newton's equations required 2 different concepts of mass. Gravitational mass determines how strongly an object feels gravitational attraction. Inertial mass determines how much an object resists acceleration. There was no obvious reason these 2 properties should be identical, yet every experiment showed they were perfectly proportional for every material ever tested. The equality was essential for Newton's equations to work, but the theory itself offered no explanation. It appeared to be an unexplained coincidence written into nature. Most scientists accepted this coincidence because the mathematics worked so well. But one person refused to ignore it. Albert Einstein looked at this strange equality and asked a radical question. What if it isn't a coincidence at all? What if the equality between gravitational and inertial mass reveals something fundamental about gravity itself? Einstein imagined a simple thought experiment. Suppose you are inside a sealed room with no windows. You feel your weight pressing you against the floor. Are you standing on Earth? Or are you inside a rocket far out in empty space, accelerating upward at exactly the same rate as Earth's gravity? Every experiment you could perform would give identical results. Drop an object. It falls to the floor in both situations. Throw a ball sideways. It curves downward the same way. Step on a scale. The reading is identical. There's no experiment capable of distinguishing between gravity and acceleration. This realization became known as the equivalence principle. If acceleration and gravity produce identical effects, perhaps they are not separate phenomena at all. Perhaps what we interpret as a gravitational force is actually a consequence of motion, specifically accelerated motion. This idea turned centuries of thinking upside down. According to Einstein, objects in free fall are not being pulled by a force. The falling apple, the orbiting moon, and astronauts drifting inside spacecraft experience no force acting on them at all. They are simply moving naturally, following the paths that require no effort or resistance. What appears to us as acceleration might arise from the structure of space itself. At first, this sounds impossible. The apple clearly accelerates toward the ground. But Einstein proposed a completely different perspective. What if the apple is not accelerating? What if it is moving along the straightest possible path available, and it is space itself that is curved? That question marked the beginning of one of the greatest revolutions in scientific thought. Einstein realized that gravity might not be a force at all. Instead, it could be a property of space and time themselves. The falling apple is simply following the most natural path available in a curved universe. To understand this, imagine Earth's surface. It looks flat to you, but we know it's a sphere. Locally, paths seem straight, but globally they are curved. Massive objects like Earth deform the geometry around them. This presence of mass changes the structure of space-time itself, creating curvature. Astronauts feel weightless because they are in free fall, following a natural path through curved space-time. Weightlessness is simply the absence of resistance. When you stand on the ground, you feel weight because the surface blocks your natural path. You aren't being pulled down, you're being pushed up. This reverses our familiar picture. Falling is natural, while standing still requires force. This bold prediction changed our understanding of light and the universe forever. This prediction was tested during a solar eclipse in 1919. Einstein predicted that the sun's mass would bend light from distant stars. When measured, the stars appeared exactly where Einstein's theory predicted, displaced from their usual positions. This provided direct evidence that space itself curves. This phenomenon is now called gravitational lensing. Massive galaxies act like enormous cosmic lenses, bending light into beautiful rings and arcs. The same principle explains why astronauts float. Gravity at the International Space Station is still 90% as strong as it is on Earth. Astronauts float not because gravity disappears, but because they are in constant free fall, moving sideways so fast they curve around the planet. In Einstein's universe, gravity isn't a force pulling things down. It's the very geometry of space and time. Earth is round because curved space-time guides matter into that shape naturally. Every object with mass, even you, reshapes the fabric of reality. Everything moving nearby responds to that geometry. The moon orbits Earth because it follows a natural path through curved space-time, not because of an invisible force. Earth's mass warps the geometry around it. This same curvature explains why a thrown ball follows a parabola. It travels through curved space-time, and the straightest path appears as a curve to us. Standing still feels like weight because the ground pushes you upward, preventing you from following your natural free-fall path. Falling is the absence of resistance. When a star's nuclear fuel runs out, it collapses, following this curvature more completely. In massive stars, space-time curves so sharply that all future paths lead inward. Not even light can escape. This is a black hole, a region where space-time itself is shaped so dramatically that escape becomes impossible. Black holes aren't visible, but their effects are. Matter accelerates, heats up, and emits intense radiation before vanishing into the void. Einstein showed that mass tells space-time how to curve. This curvature is what we perceive as gravity, guiding everything from planets to light. Newton saw gravity as a mysterious pull. Einstein revealed it's the shape of space itself. Gravity isn't a force, it's geometry in motion. Think about standing on a scale. It doesn't measure Earth's pull. It measures the force needed to stop you from following your natural path through curved space. In a falling elevator, you'd float. This weightlessness isn't the absence of gravity. It's simply moving naturally along space-time's curves. Standing still on the ground is actually a constant upward push. Once you see it, the simplest act becomes a reminder that you are part of the geometry of the universe. This perspective also explains why all objects fall at the same rate, regardless of mass. Since gravity is not a force acting differently on different objects, but rather a property of space-time geometry, every object follows the same natural paths when resistance is removed. A feather and a hammer fall together in a vacuum because space-time guides both along identical trajectories. The mysterious equality between gravitational and inertial mass, which puzzled Newton, becomes inevitable in Einstein's framework. They are not separate properties coincidentally equal. They describe the same underlying behavior. As scientists explored the consequences of curved space-time further, they discovered predictions that extended far beyond planetary motion. One remarkable outcome is gravitational time dilation. Because time is part of space-time, strong gravitational fields affect the flow of time itself. Clocks closer to massive objects tick slightly slower compared to clocks farther away. This effect is not theoretical speculation. It has been measured repeatedly using precise atomic clocks. Even GPS satellites must account for these differences. Without corrections based on Einstein's theory, navigation systems would accumulate errors of kilometers within a single day. Another prediction involves ripples in space-time known as gravitational waves. When massive objects such as black holes or neutron stars accelerate or collide, they disturb space-time itself, sending waves outward at the speed of light. For decades, these waves remained undetected, but in 2015, scientists directly observed them using incredibly sensitive instruments, capable of measuring distortions smaller than the width of a proton. The discovery confirmed that space-time behaves dynamically, capable of stretching and compressing as energy moves through it. Einstein's theory also reshaped our understanding of the universe on the largest scales. Galaxies cluster together, cosmic structures evolve, and the expansion of the universe itself can be described through the curvature of space-time. Gravity, once imagined as a simple pulling force, became the key to understanding cosmic evolution, black holes, and the behavior of light across billions of light years. Yet despite its depth, Newton's theory remains useful. For everyday engineering and most astronomical calculations, Newton's equations provide excellent approximations. Space agencies still rely on them for planning missions because they are mathematically simpler and sufficiently accurate in weaker gravitational environments. Einstein did not replace Newton by proving him wrong in practical terms. He revealed a deeper layer beneath Newton's successful description. This layered understanding mirrors many advances in science. Older theories remain valid within certain limits, while newer theories explain why those limits exist. Newton described how gravity behaves in ordinary conditions. Einstein explained what gravity actually is. And this realization leads to a profound shift in perspective. When you watch an object fall, you are not seeing a force acting across empty space. You are witnessing matter moving freely through a curved geometry shaped by mass and energy. When you look at the moon orbiting Earth, you are seeing an object tracing the natural structure of space-time itself. Gravity, in its deepest sense, is not something acting within space. It is the shape of space and time guiding everything that exists within it. Gravity is not a force that pulls, but a curve in the very fabric of the universe. When you accept this, the world looks completely different. Imagine space not as an empty void, but as a flexible landscape that shapes the path of everything moving within it. Newton saw an invisible pull, but Einstein saw geometry. The moon doesn't loop because it's being grabbed. It follows the straightest path through curved space. This is the fundamental secret. Mass tells space-time how to curve, and space-time tells mass how to move. In extreme places like black holes, the curve becomes so steep that not even light can find a path leading back out. Even time bends. Our GPS satellites actually have to adjust their clocks because time runs differently in Earth's curved geometry. Newton's laws still help us launch rockets, but Einstein reveals the deeper reality that we are living in a geometric universe. Next time you drop something, remember, it's not being pulled down. It's just following the shape of the universe. Standing on the ground, you don't feel a downward pull. You feel the Earth preventing you from following your natural path through space-time. This upward pressure is the only real force acting on you. When you watch an object fall, you see it following the structure of space-time itself. Planets orbit the sun not by attraction, but by following the curvature of space. Even light bends as it passes massive galaxies. Gravity is the architecture of the universe, the way space and time curve in response to mass. Mass tells space-time how to curve. Curved space-time tells matter how to move. Everything follows paths written into reality. Gravity isn't an external force. It is the shape of the universe itself.